So, hi. This is a combined talk by me and Soumya. So, we will be talking about how to handle load imbalance, both persistent and transient load imbalance in a distributed and a shared memory system, and what extensions have been done in CHAM++ to support this. So the outline of the talk is, first I'll start with the motivation of why we need this work. Then the solution that we propose, which is an integrated runtime system model. And finally, we showcase it on 3 different applications at a large scale, the use of this kind of integrated runtime system. So primarily, we are dealing with a lot of challenges in scaling our applications to large number of cores. So what are some of these challenges? We find that there is dynamic variations that we face each day. So these dynamic variations could be due to application itself. So for example, applications are becoming very complex, and they're using adaptive refinement strategies or irregular communication to get the most out of the today's supercomputers. So these dynamic variations in the application results in load imbalance. The dynamic variations could be due to the machine also. So for example, there is heterogeneity in the system, or there is transient OS noise or I/O happening, and even thermal and power-related dynamic variations that are happening. So all this dynamic variations result in load imbalance. And load imbalance, as we know, is one of the main challenges faced in applications to scale to large number of cores. And we know that as we are going to increase the number of cores to 1 million or more cores, this dynamic variation is just going to become worse. And the chance that even a single core is going to be overloaded is going to be high. So we need to handle this load imbalance. We talk about 2 different kinds of load imbalance here. One is the persistent, and the other is the transient load imbalance. In the persistent load imbalance, this is the load imbalance we find across different iterations of an application. If we consider an iterative application, the load imbalance that persists between iterations is the persistent load imbalance. And the other one is the transient load imbalance, which comes about due to variations in the machine or some sudden change in the application, such as OS noise, let's say. So what can we do about this? So the recent trend in the rapid increase in the number of cores on a chip results in vast amounts of on-node parallelism. So what we are trying to see here is, can we leverage these multi-core systems, shared memory systems, to handle both the persistent and the transient load imbalance while maintaining locality and lower overhead? So the solution we propose is a new integrated runtime system that combines both the distributed programming model along with the concurrent tasks. So I'll go into the details of these in later slides. And along with this combined integrated runtime system, what we will do to handle the load imbalance problem is do infrequent periodic load balancing between the nodes in the system, and do very fine-grained work sharing within the node. So we'll see in more detail what I'm talking about. So here is a schematic representation of it. Each core has a set of computations assigned to it by default. This ensures that there is locality in them. But as we can see in these colored blocks, some of the cores are overloaded, and there is a large amount of load imbalance here. So what we do is, only when a load imbalance is detected, these computation, if possible, are broken down into tasks, concurrent tasks that can be now executed by other cores within the node. So the key thing here is that by default, these computations are assigned to each core, thereby having locality. and only when load imbalance is detected do we do concurrent tasks, thereby reducing the overhead, contention, and so on and so forth. So we'll talk about what this integrated runtime system model is. For that, I need to talk about what the Charm++ model is. So Charm++ is basically asynchronous message-driven execution model, which means when a message is received, only then that computation gets executed. We over-decompose the domain into many more objects or chunks than the number of processors or cores. And these over-decomposed objects are assigned to each core. And these objects can be migrated among different cores by the runtime system, depending on various things, such as, if we detect a fault, we want to move the objects around, we can do that. If we detect load imbalance, then the objects can be moved around to handle the load imbalance problem. So the over-decomposition, as I mentioned, is decomposing the work and the data unit into many more pieces than the execution unit. So given a domain, it is divided into, over-decomposed into work and data unit, the data unit and the computation that comes along with the data unit. And these are assigned to different cores, and there are many more such data work units than the number of cores. So this encapsulation of the data and its computation inherently promotes data locality, because by default they are assigned to a core and they stay on the core and execute continuously unless the runtime system decides to move it around. Now the migratability, as I mentioned, is the moving of work units from one core to another depending on certain needs that the runtime system figures out. So what is the Charm++ SMP model? So now that we have many more cores within a node or a chip, Charm++ has been extended in the past, I believe like past 10 years, have been extended to handle the SMP model. In the Charm++ SMP model, this is to take advantage of the multi-core processors. And so basically, OS Charm process. Okay, basically there is an OS Charm process per node, and this OS Charm process launches many threads, and each thread is assigned to a particular core. There is no oversubscription here. Usually we have only one thread per core, and there is an affinity. The OS is not free to move around these user-level threads between different cores. So by default, we get an affinity of these threads to the core. This has the advantage that now we can do faster intra-node communication, because we don't have to have a double copy for moving the data between one execution unit from one core to another core. And also it results in smaller memory footprint, because now the common read-only data structures can be shared among different cores within the node. This also enables work sharing within the node. So that is the key point that we use to handle this transient and persistent load imbalance, because these cores within the node can have a shared memory. The work units can be shared between the cores. So in the integrated runtime system, we combine the Charm++ over-decomposition distributed memory model with the concurrent task to handle the load imbalance. So for that, first we have a node-aware load balancer, which basically takes care of balancing the load between the nodes, and also ensures that there is a balance between the cores as well. But the primary focus is to balance between the nodes. Once the load is balanced, any residual or transient load imbalance is handled by the fine-grained work sharing within the node. So the load balancing in Charm++ is based on the principle of persistence. So many of the HPC applications are iterative in nature. which, and based on the principle of persistence, we find that multiple iterations tend to have similar computation or communication pattern. So we can pretty much use the history, the historical information to predict what the load and communication pattern is going to be. And the load balancers use that information to do a balancing of load. So in the node-aware load balancing strategy that I'm going to talk about is pretty much a hierarchical strategy where we have multiple levels of hierarchy, and the first level is at the node level. All the cores within the node form a group in the hierarchical structure. So we basically use the hierarchical strategy because as we increase the number of cores, we don't want to have a bottleneck on the load balancing strategy. These strategies need to be scalable and also yield good load balance. In order to further reduce the memory and the communication overhead in these hierarchical strategy, we use some amount of coarsening to combine different objects and then send that information up in the hierarchical tree. And the key thing is that we can now use different load balancing strategies at different levels. For example, at the very top of the hierarchy, at the root of the hierarchy, we don't want to be doing a very from scratch strategy which moves all the objects among all the P's. Where here we would like to use a topological aware refinement strategy which keeps the objects in its place and does minimum amount of movement taking into account the topology and the communication pattern. And at the lower levels of hierarchy, we can do more better refinement or better from scratch strategy to balance the load evenly. So here is a pictorial representation of this. This is pretty much what I had talked about, where 0 to 6, it should have been 63, but let's assume there are 63 hardware threads or cores within the node. Here I interchange between cores and hardware threads, but it's basically any execution unit. They're grouped into one group, and there are multiple such groups. We have found that you usually need to have only 3 or 4 levels of hierarchy, basically. Once they form a group, the root of the node, the root of the subtree takes care of balancing the load within that subgroup, and the load balancing decisions are done from top to bottom. The another aspect of load balancing is automating the decisions of when to do load balancing and which strategy to use, because obviously load balancing incurs some amount of overhead. And unless we are doing a load balancing strategy that gives more benefit than the overhead, we don't want to be doing load balancing. So the runtime system collects some amount of statistics about the system, the application, and decides when is a good time to do load balancing. And the other one is which load balancing strategy to use. Maybe the application itself is communication intensive. Then we need to focus on the communication aspect of the application while deciding the load balancing strategy. So all this is work in progress, and basically it's a way for the runtime system to automatically detect when and what load balancing strategy to use, thereby relieving the user of making all these decisions. Now I go on to the fine-grained work sharing aspect of this. Once we have a well-balanced system, any residual load imbalance or transient load imbalance can be handled by the fine-grained work sharing mode that's happening. So here the user specifies a set of tasks that can be executed on any core within the node. We use a work stealing mechanism to distribute the task among the different cores in the system. The key thing is we don't want to be creating these tasks very often because all these cores already have computation work that are assigned to them. Only when there is imbalance detected, that's when we need to incur the overhead of task creation or overhead of the queue contention. So with the support of the runtime system, we tend to do that. There was some amount of previous work that had been done, which is CK loop based, but that doesn't take into account the runtime support to handle the dynamic deciding when to do the task creation or not. So I thought an animation would explain this better. So here is a picture of two cores that are there within a node. Let me briefly describe what these blocks are. The domain is decomposed into these objects, which are these squares. There are many more, as you can see. There are many objects assigned to a particular core. There is a scheduler on each core, and there is a message queue and a task queue. The message queues are, since Charm++ is a message-driven asynchronous model, a computation is executed when a message is received for it. And the messages are put in the task queue. So usually, the computation for each of these blocks are executed on the same core that they reside on, thereby taking care of locality. So let's say an object wants to send a message to another object on another core. That message goes into the message queue. The scheduler is doing its job of picking the message, delivering it to each object. And as you can see in the bottom part, that is showing each it's actually showing how the core is kept busy as the time progresses. So let's take this example where the message is executed and that block of work is being done on that particular core. So now the core 0 doesn't have any more work to do. But then the core 1 now picks up a message that can be potentially made into task. It notices that the other core is idle. It creates a bunch of tasks and puts it in the task queue. The core 0, which is idle, steals using the steal mechanism. We also have some other strategies, but basically if it finds that it's idle, it goes and steals tasks from the other core's task queue, pulls out the task, and now starts executing the task on its own core. So this is how we distribute the work using fine-grained tasks, only when an imbalance is detected. So there are many ways of task creation, basically. We have two different